So hi, everybody. My name is Matt Carlson. I'm VP of Business Development for a company here at the UW called Wibotic. These guys sold you a little bit of a bill of goods. I think you were expecting to see Josh Smith, who is a professor of electrical engineering here at the UW. I saw him up on the screen there a minute ago. A very prestigious fellow. We love him a lot, but unfortunately he couldn't make it tonight, so you get the biz dev guy. But basically, I'm going to give you a little bit of an overview of Wibotic and what we do. And really, if you think about what we focus on, it's power and power delivery. Unless you rode a bike here tonight, or perhaps you walked, or maybe rode a skateboard here tonight, you use some sort of what I'll loosely call fuel to get here in your vehicle. And I think most intelligent people would say that the era of fossil fuels hopefully is coming to an end. Most intelligent people would say that. But we're moving towards more of an electric economy. And the major limitation with an electric economy right now is wires. We've moved past wires with data in Wi-Fi and 4G and now coming 5G. But with power, we're still tethered to wires. Unfortunately, even with batteries, we're still plugging in pretty consistently to recharge the batteries, and the lifespan is fairly limited. So a technology was developed actually here at the University of Washington in the electrical engineering department, literally in this building, to focus on delivering power wirelessly. And it started looking at the need to do that in a reliable way under any environmental conditions, and actually was focused on the medical community at first. So we looked at initially heart pumps. So if you're in the late stages of heart failure, one of the options is to install a heart pump in your chest to help with your heart. Unfortunately, for a lot of those patients, that means having wires literally coming out of your body and plugging into a power pack. Not the most comfortable thing in the world. So initial research was focused on how could we power that heart pump through flesh, literally from a couple of inches away, and also at odd angles in case somebody happened to roll over in bed at night. You really don't want that power source to go away if it's beating your heart. So that was sort of the impetus of the technology, but then we looked at other things, other mobile devices. So the picture on the left-hand side here is a picture of a robot that was literally programmed to run itself up to a power socket and plug itself in to recharge. Not the best use of programming time. It would be much more efficient if we could just have that robot pull into a station, which today is mostly docking, but in the future could be a wireless transmission of power. So again, the concept was to have a series of transmitting devices that would effectively beam power into a receiving device. So without getting too deep into the weeds, what our technology does is we have a series of antennas, as is shown in this right-hand picture here, one of which is a transmitting antenna and the other is a receiving antenna. And today we can transmit about 150 watts of power across that gap. The gap can be several inches. You can be at various angles and not have it cause any problems. So it's a very flexible way of transmitting power in a power level that actually will power many devices. We continue to scale up, so we'll have much larger power capacity in the future. But you've probably seen that out there today, there are other wireless devices. You can set a cell phone, particularly the Samsungs, down and they will recharge. You can do it with electric cars. Some of this is experimental, but they're operating at a very high power. We focus on the market in the middle. Basically, things that operate between 50 watts and say about a kilowatt. So we focus on drones, robots, and underwater vehicles and getting them recharged and ready to go back into service as quickly as possible. In terms of vertical markets, you can imagine drones that are flying for security or robots browsing a perimeter, drones flying over agricultural areas and taking measurements. Basically, the ability to do a mission and then come back, get completely recharged, and then the very next day or even a couple hours later, run the same mission again. So in terms of lessons learned at Wibotic, they asked us to talk about a little bit of mistakes. We're still a relatively new company. We spun out 2 years ago from the UW. I can't say we've made any huge mistakes, at least not yet. I'm sure we will. But in terms of challenges, we're operating in a market that's very driven by regulations. Boop, boop. So we do have a huge, got it. We do have a huge issue with the federal government right now and allowing for autonomous uses of things like drones and mobile robotics. So that is one of the biggest challenges that we face, and then keeping ourselves focused on specific markets. So we are hiring. We're looking for a firmware engineer, so I was brave enough to put my email address up here. If any of you have those skill sets, feel free to write it down and send us your information. Thank you. Any questions?
3 questions.
Yes?
You mentioned that you have a range of several inches. Do you anticipate that will expand over the future? And what kind of safety or environmental concerns have you come up against?
Yeah, so the question was about range and specifically in relation to safety or environmental concerns. So at our current power level at 150 watts or thereabouts, there really aren't any safety concerns. But as you build up in power, certainly with electric vehicles, there are a lot of people focused on this right now. And it is going to be a challenge. So we've built technology into our product that will actually sense when we have higher power, will sense the presence of humans and will decrease the power level or shut off completely if necessary. But most of the power range we're dealing with is far less than what you'd see in, say, an MRI machine. So we're dealing with magnetic and inductive technologies as opposed to, say, microwaves, which is another way of doing this. So it's relatively safe compared to other ways of power transfer. So the question was about efficiency, how much power is lost throughout the transmission. Generally, the thing that affects efficiency the most in older inductive systems is any anomaly in placement. So that's why you have to put your cell phone right on top of the charging pad or position your electric toothbrush exactly on that charging station. We've developed an adaptive technology that basically senses when you're out of position and changes the wireless power transfer. So the efficiency levels, we've proven transfer from antenna to antenna in the 90% plus efficiency range, but then you've got electronics on both sides, so efficiency levels will drop a little bit, but 70 to 80% efficiency is really what we're targeting.
One more question.
Yep. Yeah. So the question is, power transmission drops off with distance, so why would you not want to just go ahead and plug something into the wall instead of using a wireless power system? I think that was what you were getting at. So you're absolutely correct that there are distance constraints. The technology we've developed basically expands that. So right now, where you have to have literally surface-to-surface contact, you can now deal with several inches of space. That opens up a whole new world for mobile robotics, drones that are coming in to land, for instance. It's very difficult to get them accurate within a few centimeters, but they're accurate within 10 centimeters. So as long as they can land on a station there and be within that range, we can charge them very effectively. Your question about why wouldn't you just plug it in? So with most of these technologies, they promote autonomy. We're 100% autonomous as a drone manufacturer. Well, that's not really true. It may take off autonomously, it may run its route autonomously and come back and land, but you still have to have a person there right now to swap out the battery or to plug in a battery charger. What we're shooting for is that day in the future, which hopefully is in the short-term future, when a drone can come back and land and automatically recharge itself, and say in a security environment where you're you're looking to look at a perimeter fence around an oil refinery, you can literally be in a desktop environment, launch that drone, have it run out, take a look at why that alarm went off, come back, land, recharge, and then go off to the next alarm. Today, you can't do that regulatory-wise. You still have to have line of sight and humans involved. But as drone technology and other mobile technologies prove themselves out, we think that day is coming.
All right, ladies and gentlemen, put your hands together for